Today I would like to talk about consequences of internal interaction, because so far, if we think about what kind of objects we were talking about, I mean, when we were trying to describe motion, we were talking only about two types of objects so far. What were they? The first one was obviously the particle, right? So let me remind you that for a particle, well, we know exactly what is the position. I mean, we can describe position just by giving three numbers, and concepts like translational or rotational potential, kinetic energy, for example, for a particle, or total value for a particle, really are kind of redundant, because, well, first of all, a particle cannot rotate. And, well, it occupies only one point in space. All right, what was the second type of objects which we discussed? It was a system of particles, and well, so system of particles is already in general an object. But then we concentrated on, so indeed, I introduced a system of particles, and we discussed in general. However, we never described in general motion of that system. Then we limited ourselves to a particular type of object. Because if I think about general case of a system of particles, how many numbers would I have to use in order to, let's say that I have system of two particles. How many numbers do I need to describe the position of that system? 6. I already need 6. How about 3 particles? How many numbers do I need to describe position of 3 particles simultaneously constituting an object? 9, correct. How about my body? How many numbers do you need to describe position of my body? It's not infinite. I will have to take a number of particles constituting my body multiplied by 3. Right? Okay, well, all right, so we never did that, and we won't. It's too complicated. But we recognize in engineering we often deal with a certain type of objects for which we actually were able to describe position by saying where is position of center of mass and then what is an orientation of an object. What kind of object was that? Or what kind of system of particles was that? A rigid body, correct. For a rigid body, it was relatively easy to do that. All right. Now, if I take an object which is not a rigid body, its motion is can be a little bit more complicated. And now, if I want to describe how it moves, yeah, let's take a. Can you help me with this? Hold this part. Yeah, now, I can interact with this object, for example, like that, and make it to move, right? And it moves not in such a way that the relative arrangement of the particles now does not change. It is that if I do something, that deformation moves throughout this entire system through this object. It is still a relatively simple object. It's simpler than me. Okay, so I wanted to talk about motion of such a system of particles. It's referred to as an elastic system, in which whenever somewhere strain occurs, it will affect the stresses. And how do I interact? Do I interact, for example, with this loop over here? Who believes that I do? Who believes that I don't? Those of you who think that I don't, you are right. I don't. I interact only with this part of the system. However, I affect the motion of the entire system because of the internal interaction within the within the system. This type of a motion which you just observed is referred to as a wave, as a wave motion. Now I consider actually today's lecture more like an example. So well, I came with that idea just yesterday to include that, so you don't have notes. So it's a very short chapter in the book, and if you wish, you also make notes, or just see what what's written on the slides when you look it on YouTube. All right. Now, wave is in general, it's a disturbance that propagates through space, and usually it is associated with transfer of energy. Now, this is a definition which is more general than the motion which you observed here. And I put it because waves don't necessarily have to be associated with the motion of a system, and actually a lot of waves are not. The wave which you see over here is referred to as mechanical wave, and that disturbance is really a strain. Yeah, because now if you can you hold it again? Yeah, let's hold it still, and now I will disturb it, and you saw that disturbance was traveling through it. Right, so particles over here got displaced at a certain point. You saw that a split of a second after I made a move, the particles over here also moved up and down. Did you see it? I mean, watch it. Yeah. So watch this part and compare the instant between when I move these particles up and when these will actually probably even better. Well, no, yeah, this one will be the best because I mean you will see the best over here, I think. You see, there was it was traveling that way, and we observe it over. Actually, I can maybe even show a better wave on this demonstration equipment. So I disturb just one rod over here, and you see how that disturbance travels. And now, how did it happen that it traveled over there? Yeah, because each rod interacted with the next one, and whenever this rod is turned, well, over here it applies a torque to the next one, and then that one, if this one is turned, it applies torque to the next one, and so on. Well. And here you have an example of, I mean, important thing about wave motion, that really it is, the particles don't move along the wave, I mean, together with the wave. What I mean is that if you look at this disturbance, the particles over here move up and down only. So if I think about velocity of the particles in this particular wave, the velocity of the particles is up and down. Do you see that? However, which way the disturbance moves? Horizontally. So velocity of the particles is not associated with the velocity with which that disturbance is propagated, or in other words, the velocity with which the wave travels. All right. Now, what you saw over here with the spring and over there, if it is associated with the oscillations of a medium, then we refer to those as mechanical waves. So here, I mean, these waves which I demonstrated just were mechanical waves. However, I'm demonstrating mechanical wave throughout the entire semester. You see it. I mean, actually, you don't see it, but you know, you are aware of it. How? When I speak, because when I speak, I also create a wave through, which travels throughout air, and it is also a mechanical wave. If we remove air, I can shout and you wouldn't hear anything. All right. it's not in this chapter at all, but in principle, and we can think about other waves. And well, electromagnetic waves are very well. We have applied them to in many cases. For example, even I'm doing it now. I'm using electromagnetic wave to do something. Do you know what? For example, yes, to see. In order to see, I use electromagnetic waves, and I use also artificially created magnetic field waves at this moment, because I'm using a remote, well, this remote, and my voice is recorded also remotely. It is recorded through radio waves. These are also electromagnetic waves. As humanity, I mean, as a species, we actually take advantage of electromagnetic waves in variety of applications. Well, we figured out that there must be gravitational waves. However, we haven't built an antenna for it yet. Nevertheless, because both electromagnetic waves and gravitational waves are not associated with the motion or disturbance of particles. They are associated with disturbance of properties of space. Gravitational field at a particular point and electrical field and magnetic field are affected by, these are quantities which are disturbed. All right. Now, depending on this, how wave propagates compared to the motion or the direction of the disturbance, we refer to transverse waves. And transverse waves is that if I look at a particle, all particles, then if motion or disturbance, because in general I don't have to think necessarily about position of this particle. In case of electromagnetic waves, it will be value of electric field, and if electric field or gravitational field oscillates in the direction perpendicular to the motion, which is the case, then we say that it is a transverse wave. And can you hold me this again? And here is an example of a transverse wave. Yeah, the oscillations was up and down while the disturbance was moving horizontally. We can actually have also oscillations in a different direction, that the oscillations is in the same direction as the wave is being propagated. In this case, we refer to the wave as a longitudinal wave, and I can actually use that spring also to show longitudinal wave. Okay, let's hold it. Oops, it wasn't probably the nicest. Let me try actually to do it vertically, because how about if I get higher? All right. Did you see it now? I mean, there was kind of a compression of that spring which traveled up and down. I mean, from my point of view, I really see it very nicely, particularly when it is lower. Yeah, so this type of a wave which I created now was a longitudinal wave. Sound waves actually are longitudinal waves. You have I mean, these dots represent molecules of air, and if I observe a particular molecule, look at this, for example, group over here. It oscillates back and forth. But we have areas where air is compressed and area where air is expanded. And these areas or regions travel along the propagation of the sound. Now, very often we're represented by a function. So I don't want you to look now at the plot below as a transverse wave. Really, it's a plot of the distribution of pressure along this direction. So horizontal axis represents the location. Vertical axis now represents pressure. So whenever we have higher concentration, pressure is high. Over here, pressure is low. All right, now we use mathematically we describe wave by a wave function. We can think now, I mean, consistently with the chapter, y represents the displacement of a molecule which is at location along x-axis, along x-axis, and that y component of position of the particle varies with time. So wave function actually is a function which says simultaneously what is the value of the disturbance at a particular location and particular instant. I know that usually when you think about, I mean, I know that right now when you think about waves, you immediately think about regular, well, sinusoidal function representing wave. In nature, it happens very rarely. Where, I mean, if you look at water, you would never see nice sinusoidal functions over there. The best way which you will see is probably the simulation which you saw at the very beginning. That if the water is completely still and you drop a pebble into it, well, then you will have several rings which actually will have such a shape. But sinusoidal, I mean, usually I know that somehow we develop this imagination that it is a regular sinusoidal function from minus infinity to plus infinity. In other words, that it is a sinusoidal wave. They are important. Sinusoidal waves are really important, but mainly for well, properties of nature and and properties in math. Sinusoidal functions are such functions that you can represent any other wave as a mixture of sinusoidal functions, of sinusoidal waves. So this wave in principle can be deconvoluted into a superposition of sinusoidal waves. But in general, it can have practically an arbitrary shape. I made an arbitrary shape for this wave. And if the wave travels, in order for wave to travel, the function which describes this wave has to have such a property that the value of the function at an arbitrary instant t, well, is described by a certain function which is this particular difference. It has to mix position with time. Yes, so what will be the function at instant 0? Just look at this one. Yeah, so at instant 0, let's say that this is f. So this broken line represents a plot of function f of x. When t equals 0, this term disappears. Now think actually what will happen when v times t is equal to 1. What is the plot of function of x and t equal 1? I mean, sorry, 1 over v. Well, so, I mean, when we have t equal 1, we are obtaining a new function. Do you see that? A new, yeah, because previously we had 0, now we have this parameter 1, so it's a new function. However, the two functions are closely related, because now, if I put 1 over here, so to value 0 in the new function will be assigned the same. I mean, the value of the function will be the same as in the previous one. It was assigned to what? So let's say that v times t equals, let's say, 1 meter. Yeah, so if product of v and t is equal to 1 meter, let's see what is assigned to the new function at at location 0. How is it related to the value of the original function? It was the same value as 1 less than at argument 1 meter less than before, right? So we will have that y of xt is the same as, well, it is f of x minus vt, right? Now vt is 1, right? So this is 1, which means that it is the same thing as y at x minus 1 meter at instant 0. Do you see that? All right. So it means oh, actually, I took already at x. Yeah, so how about if we think about this point? So to this point, at this point, the new function will have the same value as the old function had 1 meter earlier. I mean, earlier 1 meter back, right? Well, so if this is the property of the wave function as time passes by, what will happen now if vt is equal to 2 meters? Consult with each other. What happens with the function as time goes by? Talk to each other. Think about what happens to the plot of the function as time passes by. So we start with, let's say that at 0 it was this broken line. And as time goes by, the shape actually stays the same, except that what happens to the function? It's what? Y values get smaller. Why? Actually, it's not true. Y values don't get smaller. They are distributed differently, though. They will be distributed to the right. I think about it. Why don't we think about a function? Let's say very simple function. Yeah, so it will have just two values. Let's say that at instant 0, the function looks like that. That from 0 to 1, 2, 3, 4, 5. That this is the value of the function at instant 0, right? So it has value 0 everywhere except for interval 0, 1. Interval 0, 1 will have value 1. Now I want to plot function at different instant. How about of such an instant? Well, let's make it 2 over v. So when I multiply it by v, really I will have now x minus 2, right? Okay, so let's see what is assigned to 0. First of all, because I wanted to have product to be a simple number. So if I multiply now 2 over v, I'll multiply. Okay, let's put it differently. So how about if this v is 1? All right, and then I will put 2 here. Okay? So think now that v is 1, whatever it is. All right, so let's try now to plot the function, this one. So what is the value of that new function for x equals 0?
0.
Why? I heard answer 0. And why is it 0? Well, because it is the same value as before was assigned for minus 2, right? So I look what was assigned to minus 2, and it was indeed 0. So I'll mark that function here has value 0. Now what is assigned to 1? Again 0, because I have to check what was assigned to point 1 minus 2. So it was 0, so I have to put 0 over here. Now how about here? For 2. For 2, in that new function, I will have to assign the same value as for 0 in the previous function. Right? So it will go to 1. How about 3? 0. Whatever was assigned over there. Sorry, no, 1 again, right? 1. Yeah, so the function, the new function looks like that. And now how about 4? 0 again, right? It drops over there. Right? So if I took time 2, this is the new function. How about if I now take time 3? Let's make it 4. What will happen? It will move even further, right? So now the function looks like that. So this shape travels with time. As time passes by, it moves further and further to the right. And that displacement after time t is equal to that product of v times time which passed. That wave moves with a constant velocity. What is velocity of that wave? Yeah, in time, correct. Yeah, because now if I differentiate this function with respect to time, I will get v. Yeah, so v says how fast this wave moves to the right. This type of a wave is referred to as traveling wave. Well, we can have some other waves, like a standing wave. This is also a motion of an elastic medium in which actually we don't see motion of the deformation along that medium. And how about if I create a standing wave? Standing waves really are created if I can create two waves moving in opposite directions. So how about if on both sides I create now a wave, and you can see that nothing travels now. Yeah, when they combine together, the two waves separately, and actually for a moment you could see. And now I created a different standing wave. I can create a lot of various standing waves. I have to just move it with appropriate rate. All right. Now, sinusoidal waves are important, and as I mentioned, the reason for it is really mathematical. Whatever wave you can imagine, you can consider it as a superposition of sinusoidal waves. And actually, which sinusoidal waves are included in my voice? I mean, this is how we distinguish voices, for example. Because we say that the spectrum, we have different, each of us has a different spectrum of their sound waves which they produce. It is that not everybody produces the same combination of sinusoidal waves. If we created the same combination of the wave, we will have exactly the same pitch. And not only the pitch, but it would sound identically. But what combination we use, even if the pitch is approximately the same, we recognize the differences between the voices. Also, the same thing actually refers to light. Fact that you see colors is result of a different combination of sinusoidal waves. A sinusoidal wave, well, it also has to be a function of the same shape as for a traveling wave. Sinusoidal wave is a traveling wave, so I have to have this k minus vt, and precisely actually if I could write it down that way also, so I can write down that y of xt is equal to a sine of, and I will put k and then x minus omega over t over k times t, right? So here you recognize that I have that argument which causes that the wave is going to travel. This is not, this is kind of awkward notation by pulling this k in front. Therefore, we do it like we have on the screen. However, when I wrote over there, you can figure out with what speed the wave is going to travel. Yeah, because this coefficient has to be equal to speed. So this omega, whatever we call it, divided by k, whatever we call it, it gives us speed with which the wave travels. And I want you now to learn how to call all those numbers in that equation. And also various things in a wave. So wherever we have a maximum of disturbance, we call that that point, or more precisely it would be this phase, a crest. So if you think about waves on water, for example, so whenever you have a top of the wave, this is called a crest. You can think about it that this is the highest value of the displacement in the wave. The lowest value of the displacement is, or disturbance is referred to as trough. Now, this coefficient A says by how much the oscillation varies. So if we think about mechanical waves, is by how much the particles are being displaced vertically. Vertically to the propagation, and this coefficient is called the amplitude of the wave. The number standing next to position to a number describing position along the propagation is called a wave number. Now this is actually I mean the formula which describes a wave in our material is kind of simplified. In more general case, rather than x, I could have really the position vector, and then k would be also a vector. So I will have here a product of a vector and vector, which would result in a number, which means that what multiplication would it be appropriate for that? Scalar products, correct. So you can have a scalar product of position vector and propagation vector here, and then the propagation vector would really say in which direction the wave travels. You can also think about that it is just a well, special case when wave travels in x direction, so only x component of the propagation vector has non-zero value. So from scalar product we will of propagation vector and position vector, we will have only x component of the propagation vector and x component of the position vector. All right. Now, this vector k, I mean, think about what is the how the shape is affected. So let's say that we think about wave at a particular instance. So let's say that we will choose this instance as a reference for time. So we can say that let's consider it at instant 0, right? So this term disappears. What is the effect of k on the shape of the function? If I take k equal, let's say, 2 pi, what will be the shape? And that is, let's say that this is 2 pi, and propagation vector is measured in units, inverse units to position. So it will be 2 pi 1 over meter. Unit will be 1 over meter. So let's say that k is equal 2 pi in units 1 over, or meter to minus 1. What would be the shape of that function? Obviously, it is going to be a sinusoidal function. Now, let's draw it, right? So how about if I draw it now? So let's say that this is 0 meters, 1 meter, 2 meter, 3 meters. So what will be the value of the function at 0 meters? 0. What will be the value of the function at 1 meter? 0, correct. How about 2? 0. Is the function everywhere going to be 0? Let's try 1/2. How much? Argument will be pi, correct? Now sine of pi is 0. So, all right, how about if we try 1/4, 25 centimeters? 1, correct. Now, because argument will be pi over 2, sine of pi over 2 is 1. How about 3/4? Minus 1, correct. Yes, so the shape is going to be like that. Yeah, the mathematical period of the function is going to be 1 meter. Right, now how about if I take k equal 4 pi? I'll double it. What will happen with the function? Very good, it is going to be squeezed. Right, so now it's going to look like that. Yes, the propagation vector says not only what is the direction in which the wave travels, but also it says how it is squeezed. Well, and more precisely, actually, the larger the value of propagation vector, the more is that wave squeezed. Which geometrically, actually, it is kind of awkward. So rather than that, we use another characteristic called a wavelength, which is the distance, I mean the length of the period in space. And propagation vector and wavelength are related. Propagation vector is equal to 2 pi divided by wavelength. All right, so we covered k. Let's now go to the next number. It's omega. Omega is referred to as angular frequency. And now let's think that you sit at a particular point. How about at the origin? And think what happens with y. Yeah, if k is fixed and the 0, this function, as time passes by, it oscillates also up and down, right? Omega says, angular frequency says really how fast it moves, although it is also awkward to figure out how many oscillations we would have in 1 second from omega. However, the formulas are simpler, so we have just one number over here. Angular frequency is related to frequency, and similarly to propagation, to wave number, angular frequency is also related by a factor of 2 pi. Angular frequency is equal to 2 pi times frequency. Well, in principle, we could avoid using wave number and angular frequency. What we would do, we would just have to write down this expression with. So instead of k, we could have 2 pi over wavelength, and angular frequency will be 2 pi times frequency. You can, and in many books actually you can find out wave function written in this particular wave. Now frequency means, well, how many oscillations we have in a unit time. This is what frequency is. So if we have 10 oscillations in a second, then frequency is 10 1 over second, and 1 over second has in SI unit system has a name. Anybody knows what? Hertz, correct. Frequencies are measured in hertz, and it says how many cycles of an oscillation we have in 1 second. Well, frequency is also related, therefore, with the time it takes for one oscillation. So if frequency is, for example, 10 hertz, what is the time required for single oscillation? Yet if 1/10 of a second, this is what you said? Yeah. Correct, 1/10 of a second. Yeah, because if we have 10 oscillations in 1 second, it means that one oscillation requires 1/10 of a second. So frequency and period are related also in a particular way. Which way? They are inverse of each other, right? So period is equal to 1 over frequency. And now again, if I divide angular frequency by wave number, I will get speed with which this shape travels. We refer to this as phase speed. Now let me give you a puzzle, which you can actually solve it almost on hands. When I speak, sound travels with speed of about 300 meters. Actually, since it's late, I want you to figure it out home. Yeah, so it travels 300 meters. Now, when I speak with frequency of, let's say, about 100 hertz. How long are the waves which I produce? Sound waves which I produce. And this will be all for today, and see you Monday.